Today we'll be doing the integral from 0 to 1 of the natural log of x divided by x plus 1 dx. And to start off, we'll make the following observation that 1 over 1 plus x, the same thing as the sum from 0 to infinity, negative 1 to the n times x to the n, and it converges from minus 1 to 1. So using this fact, we have the integral from 0 to 1 of the natural log of x times the sum from 0 to infinity of minus 1 to the n times x to the n dx, which is equal to the integral from 0 to 1 of the sum from 0 to infinity of minus 1 to the n x to the n times the natural log of x dx. From here we could swap this series and integral because the bounds of integration is from 0 to 1, but it's well within the range of minus 1 to 1, so this is perfectly okay. This is equal to the sum from 0 to infinity of minus 1 to the n, the integral from 0 to 1 of x to the n times the natural log of x dx. And now we have to evaluate this sub-integral, so we can let u equal the natural log of x, which means that du equals 1 over x dx. We can let dv equal x to the n, so that v equals the integral of x to the n, which is x to the n plus 1 divided by n plus 1. This is equal to the sum from 0 to infinity minus 1 to the n times u times v, so the natural log of x times x to the n plus 1 divided by n plus 1 from 0 to 1 minus the integral from 0 to 1 of v x to the n plus 1 divided by n plus 1 times 1 over x dx. You can check as x approaches 0 and x approaches 1, this limit tends towards 0, and we're just left with the sum from 0 to infinity minus 1 to the n, negative 1 over n plus 1, the integral from 0 to 1 of x to the n plus 1 divided by x is the same thing as x to the n dx, which is equal to negative the sum from 0 to infinity, negative 1 to the n, divided by n plus 1 times the integral from 0 to 1 of x to the n dx, but that's a standard integral. We're just left with negative the sum from 0 to infinity of minus 1 to the n over n plus 1 of x to the n plus 1 divided by n plus 1 from 0 to 1. This is clearly negative the sum from 0 to infinity of minus 1 to the n over n plus 1 times an extra 1 over n plus 1, which is equal to minus the sum from 0 to infinity of negative 1 to the nth power over n plus 1 squared. So we just got done showing that our integral is negative the sum from 0 to infinity of minus 1 to the nth power divided by n plus 1 squared. From here we can perform a change of index, so we can let n plus 1 go to n, so that n goes to n minus 1, and that n is now going to start from 1, so it's equal to negative the sum from n goes from 1 to infinity of negative 1 to the n minus 1 divided by n squared. We have to recall a function that eta s is equal to the sum from 1 to infinity of minus 1 to the n minus 1 power divided by n to the s. So here clearly we have negative eta 2. There's also another result that eta s is 1 minus 2 raised to the 1 minus s power times zeta s, where zeta s is the Riemann zeta function. And so we can compute eta 2. So eta 2 is 1 minus 2 raised to the 1 minus 2 power times zeta 2, which is equal to 1 minus 2 to negative 1 power times zeta 2, which is equal to 1 minus 1/2 of zeta 2, which is equal to 1/2 of zeta 2. And zeta 2 is the sum from 1 to infinity of 1 over n squared. But that's a famous series. It's the Basel problem, which evaluates to pi squared over 6. So we have 1/2 pi squared over 6, which is equal to pi squared over 12. So we have eta 2 is equal to pi squared over 12. But we said that the integral from 0 to 1 of the natural log of x divided by x plus 1 is negative eta 2, which is just negative pi squared over 12. And this is the final result. Thank you very much for watching.